Okay, we're going to take a look at a few of the kinds of problems that you're going to need to be able to solve in relation to the first part of the fundamental theorem of calculus. So these all involve these kinds of functions that we're looking at, these area accumulation functions. So here we've got a function, g at x, defined as the integral from 0 to x of f at t dt. And f at t is this red graph that we have given, that is shown here. So g at x represents the area that we accumulate under the curve of f at t as we go from 0 to x. And what they're asking us to do here is evaluate g as a function of x for various values of x, and then use these values to sketch a rough graph at g. So we'll start, let's see, g at 1 here is the area that we've accumulated under the function f at t going from 0 to 1, or the integral from 0 to 1 of f at t dt. Well, the area that this corresponds to on the graph is just this little region right here. This is a triangle, and we can work out, base times height divided by 2, 1 times 1. So the area there is going to be 1/2. So g at 1 is equal to 1/2. We go ahead and we do g at 2 here. That is going to be, well, whatever area we've accumulated going from 0 to 1, so the integral from 0 to 1 of f at t dt, plus the additional area that we accumulate going from 1 up to 2. So we'll write that as the integral from, not from 0, but from 1 to 2 of f at t dt. Now, we know the first part here, this is just 1/2, and we're going to add to it, the region that we're going to add to it is this little region in here between our curve and the x-axis. But because this has a magnitude of 1/2, that's the size of that blue area there, but because it's underneath the curve, we have to interpret this as a negative area, because f at t has a value that's less than 0 in this interval here. So this area is going to be negative 1/2. We combine them, we get 0. So we can continue in this way. G at 3 is going to be the integral from 0 to 3 of f at t dt. We know that this is going to be the area that we've accumulated going from 0 to 2, which is 0, plus the area that we accumulate going from 2 to 3, which is going to be another negative 1/2. So we get negative 1/2 here for our answer. G at 4 is going to be that negative 1/2 plus whatever area we accumulate from 3 to 4. That's another 1/2, so we're back up to 0 here. G at 5 is going to be that 0. That's the integral from 0 to 5. 0 to 4 of f at t, plus the area that we accumulate going from 4 to 5. So we're adding in this region here. That's got an area of 1 full square plus a 1/2 square. So we'll write that as 1/2, okay, or 3 over 2. That's going to be our total area. And g at 6 is, of course, going to be that 3 over 2 plus, what are we adding on here? 1, 2, plus 2.5. 2.5 is what? 5 over 2. So we add all this up and we get 8 over 2, which is 4. Okay, so let's, on the same grid here, sketch a rough graph of this function g. Well, at 1, we'll use x's here. So at 1, our value is 1/2. At 2, it's down to 0. At 3, it's negative 1/2. At 4, it's back up to 0. At 5, we are at 3 over 2, so 1.5. At 6, we are up to 4. So that's going to be way up here. And where do we start here? Well, let's see. What is g at 0? Well, g at 0 is going to be the integral from 0 to 0 of f at t dt. That's obviously going to be 0 because going from 0 to 0, we can't accumulate any area underneath our curve. So we can add that point right there, and then we're just going to draw a nice smooth curve through these points. And there's a rough sketch of what g at x is going to look like. Okay. Here we have another area accumulation function. A at x is equal to the integral from 2 to x of square root of 1 plus t cubed dt. And they want us to calculate three things here. A at 2, a primed at 2, and a double primed at 2. And I think we'll start with a at 2. So a at 2 is just going to be, we just have to fill in x equals 2 here. It's the integral from 2 to 2 of root 1 plus t cubed dt. Just like we said on the last slide here, if we interpret this as an area accumulation function, we're starting at 2, t equals 2, going to t equals 2. Because our start and our end points are the same, we haven't accumulated any area in between. So that integral is just going to be 0. For the second part, we need to calculate the derivative, a primed of x. This is going to be the derivative, d by dt. So I think we want the derivative with respect to x, d by dx, of our integral from 2 to x, 1 over 1 plus t cubed dt. This one we can answer directly with the fundamental theorem of calculus, part 1. In it, we learned that differentiation and integration are inverse operations. So they're, in a sense, going to cancel each other out here, and we're going to be left with basically our original function here in terms of x instead of in terms of t. So this is our first derivative. Now, if we want to evaluate this at 2, we can just sub in 2, and we're going to get 1 plus 8 is 9. Root 9 is going to give us an answer of 3. Finally, we want a double primed here. So a double primed is going to be the derivative with respect to x of our first derivative. So we're going to want to take the derivative of this thing that we got for our first derivative. So the derivative of 1 plus x cubed, taking the square root of all of that. This we can do using the techniques that we learned back in the first part of the course when we were doing differentiation. We're going to rewrite the function as 1 plus x cubed to the 1/2, and we're going to apply the chain rule here. Bring down the 1/2, 1 plus x cubed to the negative 1/2 times derivative of the inner function, which is 3x squared. Then we want to evaluate this at a value of 2. So a double primed at 2 is going to be 1/2, 1 plus 2 cubed to the negative 1/2 times 3 times 2 squared. We're going to have 1/2. This is going to be 1 over root 9 times 12. Which is going to give us the 1/2 and the 12 give us a 6 over 3. So a double primed at 2 is going to be equal to 2. In the same way, we've got a similar sort of question here. Find the derivative of g at x equals the integral from -2 to x squared sine t dt. So we're asked to do the same kind of thing here. Take the derivative of a function which is defined in terms of an integral. Now, there's just a bit of a hitch in this question here, because rather than just integrating from -2 up to x, we are integrating up to a function of x, okay, x squared. This means that this g at x function here is actually a composite function. So if we're going to take the derivative here, we're going to have to use the chain rule. So one way we can sort of make this a little bit clearer is we can make a substitution. We can let u equals x squared, then u primed is going to be 2x. And if we make that substitution, our integral now becomes, or our function g of x now becomes a function in terms of u. So this is going to be the integral from -2 to u of sine t dt. Our chain rule, well, if we want to find g primed with respect to x, that's going to be g primed with respect to u times u primed. So the derivative with respect to u times the derivative of the inner function. So the derivative, g primed at u, is going to be d by du of g at u times u primed. So there's a bit more room here. So d by du of gu, we're going to be doing derivative with respect to u of the integral from -2 to u sine t dt. And then all of this is going to get multiplied by u primed. So first part of the fundamental theorem of calculus, if we're doing the derivative with respect to u and then integrating up to u, we're just going to get sine u as our integral there. And this is going to get multiplied by u primed. So our original substitution was that u was equal to x squared. So we can put the x squared back in. We know that u primed is equal to 2x. So our derivative here, g primed at x, is going to be sine x squared times 2x. So similarly, like if we see something, they ask us something like this, the derivative with respect to s of the integral from -6 to cos x u du, we can kind of just recognize that pattern, that this is going to be our cos s, or our limit of integration, cos is a function of s, subbed into our function u to the power 4. So cosine of s to the power 4 times the derivative of that inner function. So the inner function there is the cos of s. Derivative of cos s is negative sine s. And that would be our derivative. Okay, final question here. We have a function f at x shown in the graph. So our function f at x is shown in the graph below. We're defining a function a at x, which is the integral from 0 to x of f at t dt. Makes sense. Okay, it should probably be f at x dx, but that's all right. And what we want to do is find the intervals of increase and decrease for a at x and locations of the maximum, minimum, and inflection points, and the intervals of concavity for a at x. So intervals of increase and decrease, we really just want to interpret this as an area accumulation function. So if we start at 0 and we start moving our value of x towards the right here, we start by, in this region here, accumulating positive area. And we're going to keep accumulating positive area until we get up to x equals 4 here. And once we get to x equals 4, because f at x becomes negative, we're going to start accumulating negative area. So if we interpret a at x as the area accumulated, we know it's going to be increasing on this interval from 0 to 4. Then once we hit x equals 4, because we start accumulating negative area, we know that a at x is going to decrease. So it's going to decrease starting at 4 until we get all the way up to x equals 8. Because at x equals 8, we stop accumulating negative area and we start accumulating positive area again. So from 8 to 12, this thing is going to be increasing again. And it looks like after 12, this thing is going to start decreasing again. And we don't know how far it goes beyond x equals 12, so we'll just put all the way to positive infinity, assuming that the function goes on forever and ever. So in part B, where we're asked about the local maxima and the local minima, we're going to use our intervals of increase and decrease that we found in part A here. So if it's increasing from 0 to 4 and then decreasing from 4 to 8, that means that x equals 4, it changes from increasing to decreasing. So there must be a local maximum there. Similarly, at x equals 8, it changes from decreasing to increasing. So there has to be a local minimum at x equals 8. And I guess if it changes again at x equals 12 from increasing to decreasing, we can also say that there's going to be a local maximum at x equals 12. Now, the second part of D here asks us about the points of inflection. So points of inflection are going to occur where the second derivative is equal to 0. So our first derivative of our function is going to be the derivative with respect to x of a at x. And a at x is defined as the integral from 0 to x of f at t dt. Okay. We know from part 1 of the fundamental theorem of calculus that this is just going to be f at x, because the integration and the differentiation are going to cancel each other out. That means our second derivative, a double primed at x, is going to be the derivative of x, or f primed at x. So if we're looking for points of inflection, we're looking for points where the second derivative of a is equal to 0, or, in other words, where f primed at x is equal to 0. Well, how can we interpret f primed at x graphically? Well, if we're given a graph of f at x, f primed at x is the slope of the tangent. So we want places where the slope of the tangent to the graph is equal to 0. Now, where is the slope of the tangent equal to 0? Well, that's going to be right about here, and then again, right about here. So we are going to have points of inflection at, let's say the first one's about 1.5. Let's say the second one is at about 6. And the third one here looks like it's at x equals 10. Are going to be our points of inflection. Part C asks about the intervals of concavity. So we can use those points of inflection that we just calculated to set up a concavity table. So we're going to have intervals from 0 to 1.5, 1.5 to 6, 6 to 10, and then 10 to, let's go 10 to 12 here. And in this interval, we want to check the sign of our second derivative or the sign of our first derivative of f. So what is the sign of the slope of the tangent? Okay, interpreting f prime to x as the slope of the tangent. Well, if we look at our graph, from 0 to 1.5, the curve is increasing. And if we imagine drawing a tangent to it, the tangent is going to be going, is going to have a positive slope. So the slope of the tangent is positive. From 1.5 to 6, slope of the tangent, the curve is decreasing. Slope of the tangent is going to be negative. From 6 to 10, it's going to be positive again. And then from 10 to 12, it's going to be negative. So our curve, a at x, so our function a at x, is going to be concave up, concave down, concave up, and concave down on either side of those points of inflection at 1.5, 6, and x equals 10.